Throughout this course, we have built a 4-bit timer, some combinatorial logic, simple input and output buffers, and many other designs. All of these designs were a single process or logic block inside of our CPLD. But there's a great advantage we have yet to explore in FPGAs and CPLDs, and that is using hardware in parallel. If we look at our CPLD and add 3 basic logic elements, it's actually possible to have each one operate in parallel, with different inputs and outputs. In this way, each logic element is independent of the others and can be used for whatever your design requires. In this lesson, let's explore this idea of hardware operating in parallel by designing a 4-bit timer and a typical D flip-flop. The master reset and clock will be shared by both blocks, but otherwise they will be separate processes with no interaction. To start our Quartus 2 project, we'll use the new project wizard and save the project on the desktop in the FPGA/Lesson 7 folder. The project will also be named Lesson 7. Next, choose the EPM 3032 ATC44-10 CPLD logic device. Then click Next, Next, Finish, and our Lesson 7 project is created. Add a new VHDL file to the project so that we can get started coding. First, we'll need to use the IEEE libraries, specifically the standard logic library along with the unsigned standard logic library. The Lesson 7 entity will have a port with a reset input, a clock input, a push button input, an LED output, and 4 count outputs in a standard logic vector. All of the pins that connect to these inputs or outputs are defined in comments. Now we'll build the Lesson 7 architecture. Let's call it RTL. This architecture will use 2 signals, a data signal for the D flip-flop and a count value signal for the 4-bit timer. The first process will be the D flip-flop with the reset, clock, and push button inputs in the sensitivity list. If reset is 1, then data should be set to 0. Otherwise, else if the clock has a rising edge, data should be the same as the push button input. And that is the end of this simple D flip-flop process. So we connect the data signal to the LED output. The second process that we will operate in parallel with the D flip-flop is the timer. This timer will have the reset and clock signals in its sensitivity list. So if the reset is 1, then the timer count value should be 0. Otherwise, else if the clock has a rising edge, the count value signal should increment by 1. That ends the timer process, so we connect the 4-bit standard logic signal count value to the 4-bit standard logic output count. And that's the end of our architecture, RTL. Save the file as lesson7.vhd and start the compile. After the successful compile, open up the pin planner and define the pin locations. Then after you've got them all in, recompile the project. Do a quick double check to make sure that the pin planner has everything located properly, and then let's move on to the hardware schematic. This is the most complicated schematic in this course, so pay close attention. First, we start with the power regulation circuit, where a 9-volt battery inputs to an LM317. 2 resistors set the LM317 to output a regulated 3.3 volts. Then we have 2 10 microfarad bypass capacitors on the input and output, along with a resistor plus LED to notify that 3.3 volt power is good. For the CPLD connections, we connect all VCC pins to the 3.3 volt power and all GND ground pins to the circuit ground. The master reset of pin 44 is pulled down using a 10 kilo ohm resistor connecting to ground. A push button connects from pin 23 to power with a 10 kilo ohm pull down resistor on the pin 23 side. An LED and resistor connects from pin 22 to ground. Then we have a CD4511 IC and a 7-segment display. The 4511 connects to power on pins 3, 4, and 16, and to ground on pins 5 and 8. Pins 18 through 21 are the 4-bit timer output connecting to the 4511 ABCD inputs. Then the 4511 outputs connect to the ABCDEFG 7-segment inputs, and finally we connect the 7-segment LED to ground. The clock generation circuit is an ICM 7555 with pins 4 and 8 connected to power, and pin 1 going to ground. Pin 3 is the clock signal for our CPLD, going to pin 37. Then we have two 10 kilo ohm resistors and a 10 microfarad capacitor connecting from power to ground, with connections in between them going to pin 6 and 7 of the timer IC. And finally, that completes the hardware schematic. Here are all the parts we'll be using in this experiment. The larger parts are a jumper wire kit, components kit, and a breadboard. The smaller parts from the components kit are a CPLD breakout board, ICM 7555 timer module, LM317 voltage regulator, 3 10 microfarad capacitors, 2 470 ohm resistors, a 240 ohm resistor, a 390 ohm resistor, 6 10 kilo ohm resistors, a push button, 2 red LEDs, a CD4511, a 7-segment LED display, and a 9-volt battery connector. With all the parts together, let's build up the circuit. We'll use a time-lapse video of the part-by-part construction of the circuit that we just built in the schematic. Follow along and build the circuit with us. A quick point here, these three 10 kilo ohm resistors don't appear on the schematic. Using pull-up and pull-down resistors on digital control input pins is good form instead of directly connecting IC pins to power or ground, because then it prevents too much current from entering and potentially damaging the IC. Now with the circuit built, let's power it up and connect the JTAG programmer to the CPLD board as well as to our laptop computer. Then open up Lesson 7 in Quartus and using the programmer tool, find the .pof programming file and program the CPLD. Right away, the counter starts counting from 0 to 9, and the D flip-flop module turns on the output LED when I press the button. Inside of the CPLD, these two modules are separate and operate in two unique processes to achieve different goals, but they exist inside of the same CPLD. Let's get a closer look at the board. Again, the two processes don't know about each other, so they operate seamlessly and independently. Parallel hardware operation is a key element of FPGA and CPLD. If we look at a board like this one, there are many modules like Ethernet, push buttons and LEDs, 7-segment displays, and serial RS-232 output. It's not feasible to control and use all these different input and output devices with a single process. You need to use multiple modules and processes to control and interpret the data they send and receive. As an example, pretend we wanted to harness the power of parallel hardware logic to build a fast Bitcoin miner, which means performing an encryption process over and over. Inside of the FPGA, we would need a communications module to talk to the outside world, a state machine to interact with our miner modules, and then finally, all of our miner modules. The number of parallel miners or encryption modules would only be limited by the amount of free logic blocks in the FPGA or CPLD, and they would all be able to operate in parallel making it much faster than performing the same operations on a processor that must run instructions one at a time.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
In the next lesson, we'll harness the power of digital timing within a CPLD to create what is called PWM, or pulse width modulation output, and control the brightness of some LEDs.